I begin today's lecture, I'd like to take questions regarding our previous lecture materials. So do we have any question? Nothing. Okay, all right. So for those who just joined, please turn on your video. So let's begin today's topic. So lecture 4, light interaction with dielectric particles. So in this lecture, we are gonna learn how a electromagnetic wave interact with a small dielectric particles. Okay, so we begin with a very general formulation of how to solve this situation mathematically, and then move on to a more simplified version, but easy to understand. So let me begin with this motivation. So light scattering by particles. So we can think about the situation like this. In this figure, you have a, oh, I'm sorry. Seems like something's strange here. Wait a second. Let me try to. Sorry for the delay. All right. So yeah, so this is the situation. We have a particle here, a small particle here. And then a wave is coming in from left side to the right side. Okay, and you can see due to this particle, wave front is perturbed. And you can see here, there's some sort of a perturbation propagates as the wave propagates along right direction. And the question is how to solve this situation. We can think about what we've done last time. So what we've done last time was we wanted to solve the problem of reflection, for instance, reflection and transmission at a planar interface. In this case, what we did was we have a input waveform, and then we assume that there is a output wave, like a reflected wave, and the transmitted wave, right? And then because we already knew the basically the form of reflected and transmitted wave, all we need to do was just matching the boundary condition at the interface, right? So here the key was knowing the form of reflected wave and the transmitted wave, right? Because reflected wave and transmitted wave have, you know, random mathematical expression, but we knew it. We knew how the reflected and transmitted wave should have a certain form, certain mathematical expression. And all we did was just matching the boundary condition. And here we're gonna do the same thing, but it's non-intuitive. So we are gonna do it in a more mathematically rigorous manner. So how we do it, just like we did before, we decompose the system into 3 waves. So first wave is the plane wave, so which is the incident wave, right? So just this wave is just going from the left to right, and then outgoing wave which is called scattered wave. So this is basically the perturbation due to this nanoparticle outside the particle. Okay, and then the standing wave, or like the wave inside the particle. So if you add these waves, like superpose all these waves, you get the total field, right? So basically it's the same technique. It's like we divide the plane wave, planar interface reflection and transmission into incident wave, reflected wave, and transmitted wave. And here we divide it into 3 parts, which is the incident wave, outside scattered wave, and then inside wave, right? So how we do it? If we are talking about a spherical particle, like perfect sphere, we can solve it analytically, okay? So how we do it? What we need to solve is basically this equation, right? This is a scalar wave equation. And here, the k squared is epsilon omega squared divided by c squared. You are familiar with this equation. And for simplicity, we solve for a scalar wave function. It's not a, neither electric field nor magnetic field, but we solve for the scalar wave function. And that is enough, because electric field and magnetic field can be explained by, can be expressed by using a, by basically taking the curl of this scalar function. So if you take r psi and take the curl of it, this is called magnetic harmonics, which is a vector. And then if you take the curl of m, you get what's called electric harmonics. And the electric field and magnetic field basically are written as a linear combination of these vector fields, so that all you need to do is basically solve for psi. Okay, this, yeah. So what I want to convey here is basically my purpose for the first part of this lecture is not to make you understand the full details of me theory, but I just want to give you, make you understand about the flow of how this me theory was derived. Okay, so even though you don't understand specific things, you don't need to worry too much, as long as you are following the flow here. Okay, so how we do it, how we solve a time harmonic scalar wave equation. So if you have a wave equation like this, what you do is you first write this Laplacian in spherical coordinate. So r function, theta function, and psi function. I'm sorry, a phi function. And then here's the simple technique called separation of variable. So what we do is we separate psi, which is a function of r and theta and phi, as a product of r function and theta function and phi function, which is only dependent on r, theta, phi. Okay, so by doing so, we can separate the variables, and then we can obtain like multiple combinations of these functions, and then taking the linear combination of those, we can get the full solution. I guess you're familiar with this technique. So how many of you are familiar with this technique? You probably learned this from your 응용 해석학 class, or 응용 미분방정식 class. I guess that's like one of the basic classes you learn in your undergraduate, like sophomore time. Okay, so how many of you are not familiar with this separation of variable technique to solve a partial differential equation? Can you raise your hand? I never heard of separation of variable technique. 1, 2, 3, 4. Okay, all right. So okay, So I'll anyway revisit this in a more simplified version later on. So for now, you just accept that we can try this technique. Okay. So we basically what we did here is we separate psi function as a product of R function, theta function, and phi function, which are only dependent on R theta phi. Okay. So if we do so, then this equation becomes like that. And what we did here is that we basically we wrote psi as a R theta phi, and then plug that in. And because the first term only depends on R, and second term only have a derivative along D, and then third term only have derivative along phi. So only R and theta and phi function are relevant. And then what we did, and of course there's other functions multiplied here, theta phi here, and then R and phi here, and then also R and theta here. And then you divide the entire equation by R theta phi. Then what you have is here R here, and then 1 over R there, and then phi theta here, and 1 over theta here, and then phi here, and 1 over phi here, right? So why this matter? Why if you do so, then you realize that this equation, the first part of the equation, only depends on R and R function, right? And the second part only depends on theta and theta function. And then third part only depends on phi, right? So that by rearranging the terms, we can, make basically use interesting techniques. So how we do it? First, we separate theta phi versus R. So we just rearrange the term so that we have here R term, and then the other two, we have, the others. So what we did is just to, move around the term. And then here on left side, we only have R dependence. And the right side, we only have theta and phi dependence, right? So these are equal, and then we set this value to be L plus 1. Why L plus 1? Why not just some number like K? Because that's convenient. If you go follow this process. So just let's just do it like L plus 1. Okay. Now you have this equation, and then you can do the similar thing. You basically multiply sine square theta both sides, so then you have sine dependence gone, and you have sine theta here, and here you have sine square theta, and then moving this term to that side, and then moving this term to this side. Then you have this equation, right? Here you have only theta dependence. Here you only have phi dependence. So again, theta and phi are separated. And then we set this as a m squared. Okay, here L and M can be arbitrary number at the moment. So if you write 3 equations that are relevant, the first one is R equation, second one is theta equation, third one is phi equation. So now you see why we did this, right? Like by expressing original function as a product of R and theta and phi, you were able to separate the variables. So you got 3 different equations, right? And then each of these equations are easy to solve. So if you do it, so the first equation, let's see, what was the first equation? So let's look at this equation, the last equation about the phi. this is easiest equation, right? It's like a second derivative of phi is m square phi. So the solution is, of course, e to the im phi, right? That's what we know. And then the equation for theta, the solution for theta equation is called associated Legendre function. You don't need to know how it actually looks like, but we write it as this, okay? So the solution is, of course, depends on L and M, both L and M. And then cosine theta is the variable here. So this is the associated Legendre function. And then solving for R, if you look at this equation, the solution this is spherical Bessel equation. So the solution is Bessel function. Okay, spherical Bessel function. So spherical Bessel function can be divided into two classes. One is of the spherical like J equations, and then the other is called the spherical Henkel function. And the difference between these two is that the JL is finite at origin, whereas Henkel function has tends to go to decay with this form as R goes to infinity. So Henkel function is useful in describing scattered waves, and the first kind Bessel function is useful to describe a regular waves, so that incident wave and internal wave shouldn't diverge at the origin. So the spherical Bessel function of first kind is used. Okay. So and you don't need to know like all the details here, but you can just, it'll be enough if you're following the flow. And another constraint that we have is that M must be a multiple of 2 pi, right? Why this is the case? Because if you think about the system, this is your particle. Let's say this is, I'm not sure which one is your axis, but if you define, this, azimuthal direction. So let's say this is K, then the direction of propagation, then along phi direction, there is a symmetry, right? The sphere has exactly same shape, even though you rotate with respect to the propagation direction, so that and also if you have a one, let's say your wave defined at phi equals 0 and phi equals 2 pi is actually at exactly same position, right? So that they must be the same. Phi equals 0 and phi equals 2 pi. It sounds different, but it actually pointing at the same position. So their value must be the same. Oh, sorry. So then M is just an integer, right? Because when phi equals 0 and phi equals 2 pi, they must be the same. So that M should be an integer. Okay, so here's even more complicated equation. But what I wanted to say was that here now you have electric field and magnetic field of incident waves can be expressed like as a linear combination of n function and m function, right? And then Lm is defined previously. So L is defined like this, M is defined like that. And then once you have a psi function, and then by taking the curl of it, and then the and then curl of M, you get M and N vector fields, and then taking the linear combination of those, you can express H field and E field of the incident wave. And then you can do the similar thing for a scattered field and internal field. Okay, but here incident wave have a interesting constraint because we know exactly how the incident wave looks like, right? So for a plane wave with incident angle theta equals 0, so that the wave propagating like that, you know that all terms vanishes except for m equals 1. Okay, so that's like known thing, and then in this case, for the incident wave, AL1 and BL1 are just determined like this. I don't want to give you how to solve this, but anyway, for you can know that even though you express incident wave as a linear combination of spherical harmonics, because you know the incident wave is how it looks like, you can actually easily solve for it. So and then the solution looks like this. So AL, the coefficient here, is a function of L like this, and then BL is just the IL1, and here E naught, of course, the incident wave electric field amplitude. Okay, and now we express the scattered field here is and then internal field. So how do we solve this? And here we apply the boundary conditions. So these are the boundary conditions. So can you recognize what is this? So we have sphere, and then outside of the sphere, of course, there is an incident wave plus scattered wave exist. And then inside, we have only internal wave, right? That's how we define things. So along the spherical shell, sphere surface, electric field parallel to the surface must be continuous, right? That's what we know from the Maxwell equation in the first class, right? Electric surface parallel electric field must be continuous. So that's the first equation. Field outside minus field inside, and taking the cross product of R, which gives you the component that is perpendicular to R, which means parallel to the surface, right? So this is just E out parallel is equal to E in parallel. And similarly, this is the same condition. H field, outside and inside, if you take the difference, they have to be the same, right? Because there's no external current source, they must be continuous. So these two are the boundary conditions, right? And we know how the incident wave can be expressed. So we know the exact solution, exact, what can I say, the series solution of the incident wave. And we know the boundary conditions. And so by doing so, we can determine the coefficients. So AL, BL, CL, DL are all the, A, B, C, D are the components of scattered wave and the internal wave, and that can be written like this. Okay, so if you want to know the more details about this me theory, you can read this book. But what I wanted to convey here is just the flow. Okay, so what we did was we divide the wave into 3 components. we divide the wave into three components: incident wave, scattered wave, and the wave inside, right? And then we express each wave as a series of spherical harmonics. How do you obtain the spherical harmonics? We can just use a technique called separation of variables. And then once we have a series form of incident and scattered and internal wave, we apply the boundary condition along the surface of the sphere. Then we get the full series solution for all waves, all partial waves, and that's it. That's the solution for the system, right? So do we have any question at this point? I guess Matt, the full details, like for instance, why A have this specific form? Well, it's difficult to tell you at the moment because it's kind of too complicated to explain. But if as long as you're following the logic, it's okay. So do we have any question? Oh, okay, Thomas, is this solution is unique? This is a really good question, and it is unique. Yes, it is unique. So its uniqueness is guaranteed by what is called a uniqueness theorem. So you probably heard of this uniqueness theorem. If you have a system like a partial differential equation, and then you know all the boundary conditions, then the solution is unique. And of course, we need some more mathematical constraint, but typical physical system satisfies all those mathematical constraints, so it's unique. This is a really good question. And is there any other question? By the way, don't get me wrong about the fact that this is unique. So the solution itself is unique, but of course you can express the same solution using different series, right? So if you express the same solution using a different basis, for instance. So it's like this. If you have let's say you have your vector in a space, okay? And now if your system, if you set your basis along here and there, so this is your X and Y basis, then the representation of this vector is, let's say this is 3 and 4. Then 3 times unit vector along X direction plus 4 times unit vector along Y direction. So this is your vector, right? So this is one representation. And of course, if you set your axis like a completely different way, so you use some probably it's better to use some other combination. So this is your X prime and this is your Y prime, a new basis. Then of course your V is 5AX prime, right? So basically your V is same and unique in this case, but the way you express it, represent it, of course, can be changed. And here what we used is the spherical harmonics to express your solution. And if you use different bases, your solution may look different, but if you actually add them all, and then if you look at actually the field, it's the same. Okay, and the reason why we use a spherical harmonics is because it's the most convenient for this system. Okay, and any other question? Okay, so if you have a question, you can, even though I just move on, you can just leave your question in the chat box. Okay, then I'll come back and try to answer your question. And don't hesitate to ask dumb questions. Okay, even though you feel the questions may sound a little too elementary, still please ask the question. So even though you don't understand the previous part, you probably can understand this thing. So this is a graphical representation of the series solution that I mentioned previously. So this is the case of L equals 1, L equals 2, L equals 3 case. And here you have M's. Okay. And then this M and N is what I mentioned earlier. So like the magnetic and electric vector fields. And you can see here for L equals 1, which we call as a dipole, your psi, the scalar function, looks like it has a 2 pole. Right? And then when M equals 1, it's along, say, x-axis, and then it's along y-axis here, and it's along, z-axis and y-axis, right? And then if you look at the magnetic field components, if you look at here, this tells you how a scattered wave distribution, like a energy distribution looks like. And you can see when you have a dipole like this, you have the energy going in this donut shape. And here this red curve shows you the direction of the electric field. Okay, so if you look at this thing, you have a rotating electric field, which gives you magnetic field along this direction, and then oscillating back and forth. So magnetic field changing back and forth, and then creating a radiating field, and that's the dipolar component, magnetic dipole component. And in electric dipole, it has the similar form, but here, in this case, the electric field is going is in having this direction. So if you look at the L equals 1 solutions, it's all dipole contribution, right? It's just oscillating back and forth with 2 poles, and then energy distribution or radiation pattern looks like this. And L equals 2 is quadrupole. So you have 4 poles. And then because of the oscillation of these 4 poles, you have your radiation pattern looks like this, depending on different M's. And here the same similarly, when it becomes an octopole, you have a how many? 8? 6 or 8? 6, I guess. Well, anyway, you have like multiple poles, and your emission pattern looks more complicated. So your solution, basically, so if you have a particle here, and then your scattered field is a linear combination of these components, right? And then as L increases, your emission pattern becomes more and more complicated. And but what usually happens is that in typical case, dipole components dominate. So dipole has the biggest coefficient, and the octopole, quadrupole, octopole, as you go, to the higher order dipoles, its contribution becomes smaller, so that in most cases, you don't need to keep that many order. So you typically, it would be enough to keep the first order only. So only dipole term would be enough in most cases. Even in unusual cases, keeping quadrupole, up to quadrupole is typically enough. Okay, so this is how we're going. And then, yeah, Lee Seyoung asks, is M on the right side is negative number? That's a good question. Actually, M here is, because we set M as a, what is it? Let's check first. Yeah, so we set this at M squared. So even though M is negative number, the equation itself is the same. So what's happening here is that here, I'm not 100% sure, but like what as I remember, E stands for even, and then O stands for odd. So it's the same M, but as I remember, the theta components here is took sine theta. I'm sorry, cosine theta, and here, you know, this psi has sine theta terms. So that's why you have different form for different for the same M's. But yeah, that's what is the case. Okay, that's a good question. Is there any other question? Okay, so if there's nothing, I'll just move on to a more simplified version of the same thing. Okay. Oh, before then, let's look at how a actual spherical particle behaves for the incident wave. So this chart is very famous chart, which is called the radar cross section. You can just consider this as a extinction cross section, although it's a little bit different. And then you normalize your radar cross section as pi a squared, and a is the radius of your sphere. So pi a squared is just the cross sectional area. So if this is 1, that means your radar cross section is equal to the physical cross section of your particle. And if you draw this for a typical particle, and then x-axis is the size of the particle as a function of lambda. Lambda is wavelength, right? And if you look at a large particle limit here, 10 to the 2, so your particle is much, much larger than lambda, then your radar cross-section approaches to your physical cross-section. And that's reasonable, right? If your particle size is much, much larger than lambda, then everything becomes classical, so that your radar cross-section and the physical cross-section must be the same, right? But if you go to a smaller particle size, and if your particle becomes here, this is 1, so much smaller than the wavelength, then the dependence is completely different. You can see here, as the wave, the particle size decreases, your radar cross-section decreases much faster. And so its scattering cross-section is much smaller than its physical cross-section. So that's like one distinct difference to the large particle limit. And this range is called Rayleigh scattering. Okay. And then in the middle, where your particle size is similar to the wavelengths of light, it has some fluctuating behavior, right? So it's kind of difficult to tell whether it's larger or smaller. So in this regime, we call this as a Mie scattering. Okay. And then if you actually look at how the scattering pattern looks like in the Rayleigh scattering regime, the scattered light from the particle tends to be isotropic. Okay, so it's just going isotropically to the space. Whereas if you go to the larger particle limit, your scattering tends to go more and more forward. Your scattered light tends to go forward. Okay, so what I mean by forward is the direction of the incident wave. Okay, so that's one observation. And then what we try to do, so Mie scattering theory, of course, can cover all this regime because that's exact solution, that the one that I just mentioned. But there's a way that we can selectively solve only this regime and try to explain what's the this dependence, why this dependence arises. So that's what we are gonna do from now on. Okay, what's happening in the Rayleigh regime. So for very, very small particles, the phase of harmonically oscillating electromagnetic wave is practically constant over particle volume. So what I mean is that because wavelength is much, much larger than the particle, we can just ignore the phase difference within the particle, right? Because it's lambda is large and then your particle is small. So the phase difference between inside your particle is very negligible. In this case, we can apply electrostatic approximation. And in this electrostatic approximation, the wave equation, which was, can be reduced to Laplace equation, right? And then also, if you say this is your electric field, so that probably the wave was propagating in this direction. Due to azimuthal symmetry, there's no dependence on phi in this case. So what I mean here is that, let's say this is your electric field, and this is your particle, and say this is your z-axis. And then even though you rotate the system with respect to the z-axis so that you change phi, nothing changes. Everything remains the same. Your system, your boundary condition, everything's the same. So that there shouldn't be any dependence on phi, right? So your solution must be only depend on r and theta, so that separation of variable becomes easier. Like you only need to consider r and theta function. So we do the same thing. We plug this into the Laplace equation. So we plug r and theta into the Laplace equation and separate the variable. Once you separate the variable, you get two equations. One is this, and the other is this. So theta equation can be written like this. And in order to know why the theta equation looks like this, you can just look at our previous derivation here. So this was our previous theta equation. And then if you ignore this term, because phi is now irrelevant, you get the theta equation, and the same thing applies here. We set k becomes 0, so that we erase this thing, we get r equation. Here, right? So you have two equations. And the solution for theta equation is Legendre function. So here, note that there's no M dependence because there's no M. Phi, there's no phi dependence in the system. So you have Legendre function. And then solution for our equation is even easier. So you can see here, R is either R to the L or R to the minus L plus 1. Two cases, right? And then if you actually try to write the potentials inside and outside the sphere, inside should look like this. So PL cosine theta is the theta function. And then RL, R to the L is the R function. And then AL is just the coefficient. And you have a linear combination, so basically making a series. And then outside, you have the same form, but you can have like two choices of R. Like it can be either R to the L or R to the minus L plus 1. Okay, so that you need two kinds of coefficients. So here's one quick question. Why we cannot have R to the L minus L plus 1 for the inside field? Can you answer this? So outside, we said it's a linear combination of R to the L and R to the minus L plus 1. But inside, we intentionally didn't include R to the minus L plus 1 term. Why we did that? Can anyone answer this? Yes, thank you, Kim Chae-yoon. Yes, as Kim Chae-yoon said, because if we have R to the minus L plus 1, this diverges when R goes to 0. And then inside solution, of course, has the origin, contains the origin. So the field cannot be diverging so that we cannot have this terms. That's exactly correct. And so, right, and then now, if you look at the outside field, what we know is that, let's say this is the particle, and then let's say this is your EZ, right? And what we know is that when R goes to infinity, so when our position is very, very far from our particle, then EZ must be, E must be equal to, say, E0 along Z direction, right? So what I mean is that if we are far from the particle, the electric field must be same as unperturbed field, which is E0 along Z direction, right? So so that phi must have this form, minus E0Z when R goes to infinity, right? Because phi is the potential, the scalar function. So electric field is just a gradient of it, so that minus gradient of it. So if you, in order to have electric field to be E0 along Z direction, phi must have this form. And then from this relation, we know that B1 is minus E0, and then all the other terms must be 0. And how this is clear is if you look at this here in this term. When R goes to infinity, all these terms becomes irrelevant. So that from this boundary condition, we cannot determine CL, right? No matter what value CL have, it wouldn't affect the boundary condition at the infinity. But if you look at this, when R goes to infinity, we know that psi out must be minus E0Z. So in order to satisfy this condition, L larger than or equal to 2, PL should be 0, right? And then only L equals 1, PL can have some form which is E0, right? So that B functions are determined. B coefficients are determined from the boundary condition at the infinity. And then tangential component of the E field are continuous along the interface. And then normal components of D field are continuous. So you have this E field is continuous, and this normal D field is continuous. And how do we apply that condition? Of course, if you have a phi function, the potential function, if you take the partial derivative along theta, you get surface parallel component. And then if you take the derivative along R, and you get a D component, right? You should remember E is minus gradient of phi, so D is epsilon E, right? So by using this, you do know that E theta component is actually same as minus phi d theta, right? And do the same thing. And so from these two boundary conditions, you can obtain these two relations. And then once you get these relations, you can determine like all the other coefficients. So what I mean, all the other coefficients are basically AL and CL, like these coefficients are determined. Okay. And that's it. So in this case, in this example, we obtain the solution, the exact solution of a small particle case, and that's written like this. Very simple. Even though we said we began with series solution, once we solve it, we know that okay, it only has one term alive, and all the other terms are actually coefficients are 0. So inside and outside. Okay, inside we are not too much interested, but outside we can see there are two terms. So the first term is about what corresponds to the incident field, right? Because this is basically when R goes to infinity, this term gives you E equals E0Z, which is the incident field. So that the second term is the difference, is basically the perturbed field due to the particle. And then if you look at the form of this, it's actually can be written like this. So it's basically the dipolar potential. Okay, so here if we write this equation into this form, then we determine what's the dipole moment of this equation, and dipole moment can be written like this. Okay, so we basically equate this term to determine dipole moment, and then we know that dipole moment and the applied electric field have this relation. So basically electric field multiplied by polarizability is dipole moment. Okay, so that from that you can obtain the polarizability. Okay, so the polarizability looks like this. So now if you look at the polarizability have 4 pi a squared. So it's 3V, which means the 3 times the volume of the sphere multiplied by the permittivity of the material inside and permittivity of the material outside So EM plus 2ED and EM minus ED. Okay, so that's the polarizability of the system of this particle. Okay, and now if you look at the scattering cross-section, polarizability and scattering cross-section have this relation. Why? Well, I don't want to explain in detail, but if you have a polarizability like this, then the emitted field due to this oscillating dipole is proportional to the square of the polarizability. And then so if you draw that, and also k to the, here's another dependence of k to the fourth. So the scattering cross section, if you look at this equation, is you can see here is proportional to the cross sectional area. This is the physical area times 2 pi a over lambda fourth power times this, this combination of the permittivity. So what this tells you is that the scattering cross section of a small particle is proportional to the fourth power of 2 pi a lambda, right? So that's why we have this dependence. So this actually is the fourth power. You can see here, this axis is logarithmic scale. So this is actually the fourth power of the particle size. Okay. So what I just, if I briefly recap, what I just did was, in order to know why a small particle has this dependence in terms of a scattering cross section, we tried to solve the particle scattering problem in a very small particle limit. And in a very small particle limit, electrostatic approximation is valid. So the equation becomes much more simplified. And then you can actually get an exact solution. And this is the exact solution. And from the exact solution, if you look at the potential field outside, the potential field outside is composed of two terms. The first term is the original field or incident field, and the second term is the scattered field. And the scattered field have a form of a dipole potential. And from this, you do know the polarizability of this small particle. And this polarizability have this form, right? Is proportional to the volume of the particle. And then scattering cross section is proportional to the square of the polarizability and fourth power of the k vector. So if you combine them, you see the scattering cross section is proportional to the fourth power of the size of a particle. Okay, so that's a simple derivation of why in Rayleigh approximation, why in small particle limit, your scattering cross section is proportional to the fourth power of the size of the particle. Okay, so now if you go to a oscillating dipole, you can you basically simply multiply e to the I kr. Then you can actually obtain the magnetic field and the electric field associated with electric oscillating electric dipole. And if you look at the near zone and the radiation zone, your magnetic field and electric field can you can basically obtain the exact mathematical form of electric field and magnetic field due to a oscillating electric dipole. Right. So do we have any questions so far? I hope this is a bit tedious and complicated for those who are not familiar with all these mathematical techniques. But I guess at least the second part is not too difficult to follow, because the problem is significantly simplified. So I guess it's much easier. Any question? Nothing? Okay, then I'll try to tell you what's the result of this Rayleigh scattering. So if you look at a sky, you know, the sky is blue and the sunset is red, and then if you can associate that with the Rayleigh scattering. So based on the Rayleigh scattering, let's assume that your particle size is the same. If you have the same particle size, then because Rayleigh scattering cross section is proportional to 2 pi a divided by lambda. So if a is the same, when lambda decreases, I'm sorry, it's 4. Lambda decreases, your scattering cross section rapidly increases, right? So what this means is that blue light are scattered much more than the red light, right? So how does that make your sky blue and sunset red? It's like this, okay? So what we do is like, I think this is a bit misleading, but anyway, you have sun here, okay? Sun has all spectrum of light, like blue to red, and then what you are looking at is not like let's say when you say sky is blue, in this case is that you are looking at like here, not directly to the sun, but like the sky, like here. And then what you are looking at is actually the light scattered by the atmospheric particles, right? And then as I said, scattering in the blue side, blue light is much more efficient than the scattering of red light. If you're just looking at the scattered light, what you see is blue, right? Because it's you're not looking at the direct light, but you're looking at the scattered light, so it's mostly blue. And then in the sunset or sunrise, the situation is a little different, because what you are looking at is actually around the sun, right? So you're basically seeing 1 minus blue in this case. And also in this case, you are the how can I say, the depth of the atmospheric layer is much longer than the case of the midday, so that most of the blue light are just scattered off, and then what you can actually see is red, 1 minus blue. Okay, so that's why sky is blue and sunset is red. And if you actually look at this case, probably sun is somewhere around here, right? And then if you look at above, so if you look at this part, of the sky, what you will mostly see is the scattered light, right? So it's still blue here. And then if you look at more directly to the sun with more length of a atmosphere, it becomes 1 minus blue, so that it's red, right? So that's how Rayleigh scattering works. And then in the extreme limit, you can think of you can see this example of September 2020. This is a real photo in the daytime. So in September 2020, there was a largest wildfire in California history. And if you look at, so this is a photo of Golden Gate Bridge, San Francisco, and in daytime. But like due to the fire, there are so many small particles in the atmosphere, so that it's basically become its effective thickness of the atmosphere increases a lot. So in this case, blue light is just all scattered off, and you can only see is the red, which is less affected by the scattering event. Yeah, so do we have any question? Yeah, so from now on, I will try to explain a little more details of how we can actually utilize the electromagnetic response of a small particle, like in the regime of Mie resonance. And that's basically another topic. Like we are here, I'm gonna talk about this regime. So before I switch the gear, I'd like to take questions. Okay. If we have no question, then I think I can stop here.